in first attempt, because even successful mathematics starts with zero. Everybody is genius in their own way. But if you judge a fish by its ability to climb a tree, it will spend its whole life believing that it's stupid. That is the famous quote by Albert Einstein. Well, no other person's word would be better than his to start today's event. Good morning, everyone. On behalf of Department of Physics and Electronics, Rajdhani College, I Megha Sharma
and I Karan Vashisht,
your host for the day, extend a warm welcome to all of you present here.
to begin the event on an auspicious note, I request Sir Professor Patrick Das Gupta to come on the stage and light the ceremonial lamp. I also request our principal Sir Dr. Rajesh Convener of Society, Sir Dr. S.K. Dhaka, and Teacher in Charge, Department of Physics and Electronics, Sir Dr. A.P. Singh, to accompany him.
I'm also a part in organizing this program. I would like to thank Dr. S.K. Dhaka just to organize this program on such a latest topic which relates to the Nobel Prize of this year in physics. In fact, a couple of days before we had a program of chemistry department, and that time also I had something in my mind. Instead of organizing a program on routine kind of topics, if the content, if the topic is as latest as we are going to share today, would benefit a lot. And I would also request to my other colleagues in different departments to continue this kind of approach before organizing the program on their different platforms like Chemistry Society and other social science departments. Who are in the first year, they may feel how it will benefit us, these kind of programs. My young friends, limiting to content of the curriculum and regular classroom teaching and studying, these are the occasions when you just widen our horizons by attending such lectures and that of a teacher who is a teacher in real sense, who is so humble, and he's been so kind to be with us in previous years also. And as I'm told by Dr. S.K. Dhaka, in a very short time it was all arranged. So it again, I mean, his humbleness and true teacher in real sense. Sir, we are very grateful to have you here. And one thing I would also like to add on this occasion, that as you know, I mean, few months back I took over as head of the institution. So the kind of concern and kind of affection, although I mean I should be rational for each and every student, but what I realize in particular, that all of you, the physics honors student from first year to third year, electronics also, I mean, automatically I have created a very different kind of bonding. Although I don't recall the name of many of you, but obviously I am familiar to most of you. Reason being, I teach first year, so I am familiar with all of you who are second year and third year also. And it gives me a sense of happiness to whom we are teaching. They also started having a sense of belongingness. Few days back, one student came to me. He was waiting outside. He did PhD from the Department of Physics. He did BSc from our college, and he wanted some help. So I started going in the flashback, and I could recognize him. Yeah, obviously I have taught him. So when he when he mentioned his name, I could realize he was our student. Then I shared. I mean, he is PhD. submitted his biodata to me. I was so happy. Immediately, Dr. A.P. Singh came to the principal's office. I handed over the biodata to him. We discussed his academics. He equally appreciated him. So, the reason just sharing this feeling is, if you do good, we equally feel good. So every time I used to say, branding does not belong to the principal and the building of this college. It starts from all of you. So really, I acknowledge the way you are doing as a physics student in the college, and I have seen most of you, this Jatin, I think, sitting in the reading room in the late evening. And I feel so glad. I am a regular visitor by and large to the reading room also. It starts opening till 8 p.m. in the night. So I take this opportunity to thank once again and welcome Prof. Patrick Das Gupta, and once again appeal to all of you, please start creating a sense of belongingness to the college. If something you feel, you see wrong, you must have a kind of sensation. This is my home, this is my college, and I will feel I am going to be successful if I as a teacher also could inculcate this kind of element in all of you. I am really happy today with all of you, and the kind of cooperation in terms of maintaining the discipline as the students. Once again, thanks a lot and wish you all the very best.
As predicted by Albert Einstein, in this theory of general relativity, gravitational waves were first experimentally detected almost 100 years after he proposed it. Being a little superstitious, I do not believe that this is a mere coincidence. The Laser Interferometer Gravitational Wave Observatory, or LIGO, for short detected the first gravitational waves in the September 2015, shortly after its first search. As principal sir also mentioned, more recently the Nobel Prize in Physics for the year 2017 was awarded to three people, Kip Thorne, Barry Barish and Rainer Weiss, who were pioneers of LIGO, for decisive contributions to the LIGO detector and the observation of gravitational wave.
Please begin his lecture and enlighten us more on the topic of gravitational waves.
Thank you for the kind introduction. So I start by thanking Professor Giri, Professor Dhaka, Professor A.P. Singh for giving me opportunity to speak and interact with you. And it is always heartening to see one's students in the faculty of Rajdhani College. And I also know various students who passed out from Rajdhani College who have done quite well in the field of research. Of course, the topic today is of current interest, particularly because, as in the introduction itself, it was told that Albert Einstein had predicted the existence of gravitational waves about 100 years back, and only in 2015, the first direct detection of two massive black holes merging and releasing huge amount of radiation in the form of gravitational waves was discovered, and which was reported in 2016, and it created a big furor in the world of physics. And immediately it was followed up by another event. The first event was maybe this is better?
Yes.
So, immediately after the first event, in December 2015, the second direct detection of gravitational waves was made, and there has been no stopping since then, because on the whole, 2 more detections were made, and right now we have 4 black hole mergers from which gravitational waves have been directly reported. And because of all these, this year, these 3 gentlemen who were primarily the motivating people for the LIGO received their Nobel Prize in Physics. Now, let's go to the very beginning. Our ancestors, of course, knew about the existence of space as well as time. How did they come to know about the existence of space? Very easy. Supposing I want to touch the wall back there, I can't touch from here. I have to go all the way to the wall to touch it. That means there is a space between me and the wall. So existence of space is easily discovered, and our ancestors did it about 5,000, 10,000 years back. Similarly, time was also discovered by our ancestors. Again, how? Because we know events happen. I am talking some event, after that talk is over, and you will all, at the moment itself, you are feeling hungry and you want to soon go and have your lunch. So events keep happening one after other. And furthermore, human mind registers all these events, and we record them, and we know about our past. We at the moment feel about the present, but future cannot be predicted, except classical physics. Some part we can predict it, but in general you can't. And therefore, we know that time exists. So our ancestors had also found out that time indeed exists. So therefore, it's an interesting question that if space was completely homogeneous, no discreteness, could our ancestors have discovered the existence of space? It's a good question, but it's a metaphysical question. Why? Because you can't test this. If everything was homogeneous, there won't be human beings. After all, we are distinct human beings, we are discrete. So inhomogeneity is guaranteed. So we can't test this question. And because there is space, in order to know about what lies further away, some external agency has to bring the information from an object somewhere to our sensors, our eyes, our mind. And for distant objects is the light which brings the information. So therefore we see that space, time, they get united in the form of speed of light, which makes the time also into a space. And special relativity essentially use this idea to completely change our idea of space and time. So, for classical physicists, of course, the space-time was background. It did not change. It was like a fixed arena where matter played out its role. But for relativists, is a space-time which is more important than the matter which is acting like actors, and that's the reason why this quote is more apt for general relativists, for whom the scenery of a play is more beautiful and actors just obstruct the view, and we only get to see the actors unnecessarily obstructing the scenery. Of course, matter should not be discarded either, because after all the magnificent things that are playing out, including ourselves, are all due to matter. So we know that theoreticians have speculated about very tiny objects the size of the order of 10 to the minus 33 centimeter called Planck length, things like strings. Some people like Yogeshpati, they have talked about prions as the fundamental particles, but these are all speculative. We don't know whether they really exist. But after that, we have leptons, electrons, muons, neutrinos, then protons and neutrons, which are made out of quarks. So neutronics has been inspired by the neutron, which has, as you know, 3 quarks, UBD quad. And then of course, particle accelerators have discovered many fundamental particles like W boson, Z boson, etc. And all these fundamental particles combine to form atoms, molecules. These atoms and molecules, although they are neutral, because of the electrical dipole moment, they bind with each other due to essentially van der Waals forces, and they give rise to very complex molecules like DNA, RNA, amino acids. Finally, all these combine to form living cells, primitive living cells like amoeba and chlamydomonas, etc. But then they organize themselves into tissues, bigger living, multicellular living systems, and in the course of Darwinian evolution, the higher and higher forms of living systems are created, primates like chimpanzees, gorilla, and finally human beings who are able to think and comprehend the laws of matter and space and time, which themselves have created our brain and our mind. So it's very fantastic that we are trying to understand matter. So we ourselves being created out of matter. So as though matter is trying to understand matter itself. It's a very philosophical question. Then if one goes to large scales, gravity starts dominating. Why does gravity dominate? Because unlike electromagnetic forces, unlike other forces, the gravitational charge, what is gravitational charge? The energy or mass. Mass is never negative. So therefore, you cannot neutralize gravity. For example, electric field can be neutralized because if your electric field is created by positive charge, then you can dump negative charge particles and neutralize so that the electric field disappears. But gravity cannot be neutralized because there is no negative mass particles. And therefore, mass being additive, from the cell, doesn't matter, the cell probably is good. Doesn't matter, I'll keep continuing, I think I'll be still audible. So, mass being additive, what happens is that when you put in more and more mass, the total mass increases, and gravitational field being proportional to gm by distance. As mass increases, gravitational field also increases, and therefore as you increase the mass to the level of moon or bigger objects, gravity becomes dominant, and the gravity being a central force, it tries to attract everything towards the center, and that's the reason moon, planets, they are almost spherical in shape because they have crushed out all other forces because gravity is a central force. And then the whole matter in the universe is organized in terms of 10 to the 11 to 10 to the 13 stars, and there are elliptical galaxies which are featureless. These are all stars, they are all bound due to the self-gravity, while you can have also spiral galaxies with arms, spiral arms. Here is spiral arms, and if you peer into the night sky using a powerful telescope like a Hubble Space Telescope, you see the grandeur of the universe. And because they are mass dominated and big scales, gravity is the sole force that dominates. In other words, that when you go to scales from moon and planet, then gravity is the arbeiting force. You have stars, galaxies containing more than 10 to the 11 stars, clusters of galaxies. Rich clusters have almost 1,000 galaxies, superclusters having 40 to 50 clusters of galaxies, voids, great wall, and the whole universe at large scale is a very fascinating entity altogether. We are just a tiny speck in the whole universe. So this is the grand view of our universe. Now, I won't go into the details of relativity. All you know is that special relativity unified time with space. So in other words, the space-time, which is a four-dimensional manifold, is where all the action goes. So therefore, instead of giving just 3 coordinates of a point, you have to give 4 coordinates, that is where an event happened and when the event happened. So the whole play of the universe is being carried out in a 4-dimensional manifold. So, and one of the fundamental postulate which has been again and again tested in experiment is that no matter whether the source of light is moving towards you or whether you are moving towards the source of light, if you measure the speed of light, it is going to be always 3 into 10 to the 8 meters per second. And once you take that postulate and the second postulate, which says the mathematical forms of physical laws remain the same no matter in which inertial frame of reference you study the laws of physics. And with this, you can prove all the fascinating results of special relativity, namely length contraction, time dilation. If you have a object whose rest mass is m0, it is moving with speed v with respect to u, then if you measure the mass, its mass will be m0 divided by 1 minus v square by c square, and this immediately tells you that nothing can move faster than the speed of light. Why? Because if v becomes greater than c, mass becomes imaginary, but no measurable quantity can be anything but real, nothing can be imaginary, and that itself tells you that nothing can move faster than the speed of light. And it's an easy exercise, because if m is m0 divided by square root of 1 minus v square by c square, then m0 is m into square root of 1 minus v square by c square. That tells you that if v is equal to c, then m0 must be necessarily c. That means only those particles can move with speed c whose rest mass is 0. So photon having a rest mass 0 necessarily has to move with speed c. So therefore, what we have I won't go into all that. So Einstein completely changed our notion of space and time. But then he realized that Newtonian gravity cannot be correct. Why did he realize that? Because according to Newtonian gravity, the force between two objects is gm1 m2 divided by d square, where m1 and m2 are the masses of the two bodies, and d is the instantaneous distance between the two objects. So therefore, if one object is to move now, the other object will immediately see the change in the force now itself. Okay? So in other words, what I am saying is that if sun were to disappear today, just now, if sun were to disappear, then I will see no gravitational force and earth will be flung tangentially, but I will keep on seeing the sun, because light takes 8 minutes to come from sun to earth. So although sun has disappeared now, gravity disappears now, but I'll keep on seeing sun for the next 8 minutes, because light will still be coming in. But there's a contradiction with relativity. So therefore Einstein realized that Newtonian gravity cannot be correct. If there is a change in gravity, this change can at the most propagate with speed of light. It can't be instantaneous. And therefore, for 10 years he struggled to create a theory of gravity that is consistent with special theory of relativity. Okay? And he used the idea of equivalence principle. Galileo, who is the father of physics, who lived 400 years ago, he demonstrated, he threw out one of the wrong laws due to the Greek philosopher Aristotle, who had said that heavier things fall faster than lighter things. But Galileo, he was the father of physics. He realized that you can't just base things without experiment. You have to do experiments to find out what are the right laws. So he took to the top of the Leaning Tower of Pisa and dropped a 20 kg object and a 40 kg object from the top at the same time, and demonstrated both landed on the ground at the same time. So therefore, the gravitational acceleration of objects do not depend upon the mass of the object. And Einstein used that to realize, remember, anyone could have realized it, because Einstein was a genius, who realized that because of this Galilean equivalence principle, if you go to a frame of reference in any arbitrary gravitational field, and if this frame of reference freely falls, then inside the frame gravity disappears. Why? Because if I am outside this frame and my friend who is sitting in a frame which is freely falling, I will see that everything in that frame is falling down with 9.8 meter per second square acceleration. So therefore, my friend who is in this, he will see that nothing is accelerating, and therefore gravity has disappeared for him. In fact, astronauts, when they are being trained for zero gravity, that's what they are trained, that's how they are given the training. They are taken in a aircraft very high, and the aircraft freely falls, and everyone experiences zero gravity. This was for the first time understood, realized by Einstein, although anybody who knew about Galileo, knew about Newtonian gravity, could have understood it. And he realized that this is the key thing which has to be used to make a gravitational theory that is consistent with special theory of relativity. There's another way of saying the same thing, that is, if you go very far away where there are no matter, okay, when you are very, very far away from stars, galaxies, then since you are very, very far away from matter, there is no true gravity. But you can simulate gravity by making your rocket accelerate upwards with an acceleration 9.8 meter per second square, then you will start feeling a gravitational force-like force pushing you down with exactly same gravity-like feature. So this is also another way of stating the equivalence principle, meaning a person who is at rest on the surface of the earth and a person who is not in any true gravitational field, but if its rocket is accelerating upwards, no experiment can distinguish whether a person is accelerating or a person is at rest in a gravitational field. So therefore, Einstein, realizing this, he immediately realized that there is something to do with geometry. So Einstein not only had unified space and time into a single entity, Einstein with his general theory of relativity unified physics with geometry. How did he do that? Let's go. So we all know from our mathematics, from our school days, we learn Euclidean geometry, where if you have a flat sheet of paper, then you can draw two parallel lines which will never meet. But then later on people realized Euclidean geometry is a very special geometry. They don't hold good on curved spherical surfaces. For example, if you take a football and draw straight lines, what will be the straightest possible line on a football? It will be a segment of the great circle. Great circle is like the longitude. That means great circle is obtained by taking a plane passing through the center of a sphere, and wherever the plane intersects the sphere, that's a great circle. For example, longitudes on Earth, they form a great circle. And they are the straightest possible lines on a sphere, and we know that if you take any two great circles, they have to meet. After all, we know longitudes, they meet at North Pole and South Pole. So there are no parallel lines on the surface of the sphere. Similarly, you can consider another two-dimensional surface like the saddle, horseback saddle. There you can draw infinite number of parallel lines passing through 2 points. So therefore there are all kinds of geometries in the world. But what is to do with gravity? Now, mathematicians had already realized no matter how curved a surface is, you can always take any point and go to a small region. That region will be like a flat tangent plane. So therefore, although the surface is not a Euclidean surface, the geometry globally is very different, but locally, if you draw a tiny disk on a curved space, in that tiny disk, Euclid's geometry is valid. You don't have to know non-Euclidean geometry. If you take 2 points, the distance between the 2 points will be dx square plus dy square, just like in Euclidean flat sheet. So in other words, in mathematical geometry, you already know, no matter how the curved the space is, you can always take tiny region where the geometry is like the flat geometry. What does it remind you of? Einstein's realization that no matter how strong or how non-uniform gravity is, in a freely falling frame, gravity disappears. Immediately Einstein connected. So therefore, gravity must be framed in the language of geometry, and local inertial frame where gravity disappears is where the geometry is flat, like special relativity geometry. So therefore, Einstein realized that in a local inertial frame, you don't have to know gravity. All you can do is learn special relativity and do your special relativity in this local inertial frame. But local inertial frame is local. The moment you want to go to global region, you need tensor calculus. So, to understand general relativity, you have to learn tensor calculus and learn special theory of relativity very well, which says nothing can propagate faster than the speed of light, and immediately you know that gravity consistent with special relativity means there must exist gravitational waves. Why? So this picture, this painting is by the poet Robert Blake. So after I thought that it fits in with general relativity as though God created the entire space-time using geometrical elements. I want to just tell you why gravitational waves has to exist if special relativity is correct and is applicable to gravity. Imagine you have a massive body and a lighter object going around the massive object. Then if you are sitting here and measure the gravitational field, the gravitational field will be changing with time. Why? Because the distance of this object from you will be changing, it will be going like this. So when it is here, it will be further away. When it is here, it will be closer by. So even Newtonian gravitational field will be changing with time. But special relativity says that changing gravitational field cannot be instantaneous. It has to propagate with speed of light, and therefore the gravitational field must propagate like a wave, and that is what is gravitational wave, except that according to general relativity, gravity is not a force, but it is manifestation of bending of space and time. And there were many predictions of general relativity, namely redshifting of light. That is, Einstein proved that clocks run at a slower rate in strong gravitational field. So therefore, if you send from the surface of the earth upwards, the wavelength will get stretched, because here the frequency should be higher, it's ticking faster. At higher level the frequency should be lower, and therefore the wavelength will get stretched. This has been experimentally tested using Morse-Bar spectroscopy by Pound and Röpke. And then Einstein also predicted that light will, when it goes by a very massive object, it gets bent, and that also leads to gravitational lensing. And that was the first test that was carried out by Eddington's scheme. So what it means is that supposing there is a star here and the star is behind the sun, so you can still see the star although it is behind the sun, because the light ray, as it goes, it gets bent and you will see it here, but you will think the star is here because you will just draw a tangent, and the direction of the star, the apparent position of the star, you will think is here, although the real star is here. And this prediction was verified by Eddington's team way back in, I think, 1919, just 3 years after general relativity. So therefore, there were many predictions like gravitational waves, etc., black holes. Big Bang model itself was a prediction, and there is young people might be interested to know that there is another prediction called wormhole. That means what? That if you are here, you can immediately go to a distant part of the universe just by going through a tunnel. But wormholes, existence of wormholes require that you have strange kind of matter with you. How strange? The matter must have negative pressure. You all who are learning thermodynamics know that pressure can never be negative. For ideal gas, pressure goes as NKT. Temperature is positive, number density is positive, Boltzmann constant K is positive. So pressure is always positive. So in order to create a wormhole which will warp the geometry so much so that the curved geometry will create a tunnel between this region and very far away region, so that you can just tunnel through. And this theoretical possibility, if you have negative pressure, also has been shown to be unstable. Even if you have matter which has negative pressure, you can create a wormhole, but it will be unstable. It will immediately collapse to black hole. So those problems are there. But what was interesting is Kip Thorne showed that if you have a wormhole, you can create a time machine. It's a very simple thing. All you have to do is make one end of the hole accelerate upwards. Then twin paradox says that an accelerating frame, time goes slow here. Time will not go slow here. Time will be going slow here. So if you go from here to there, you will go into future, because here the time is going slow, here the time is going in a normal way. So you can go from present to future, while a person in the future who is here, if he goes through the tunnel, he'll go to the past. So therefore, if you have a tunnel, which is called a wormhole, you can create a time machine. But time machine, as you know, has a paradox associated with it. What is the paradox? So-called grandfather paradox. The paradox is this, that supposing you have a time machine, you can go back 1 million years back when dinosaurs were ruling. There were small mammals like small, rodents, rats. There were no higher mammals, but you go 1 million years back, kill all those mammals. You kill all the mammals. Where did the mammal which gave rise to human beings came about? After all, you invented the time machine to go back and eliminated the very cause that created you. So it creates paradox. So time travel creates paradox, and it ties up nicely with the fact that wormholes are unstable. So in today's understanding, you really cannot build a time machine, although our friends here are very happy that they have created time machine. Some young people might be watching a very comic serial called The Big Bang Theory, where one Indian also plays a very important role, and they are very happy that they have created a time machine. Let's not go into, the time is short, so in other words, what Einstein generally says is that if you have two massive objects connected by a spring, and if one is having charge q, the other is having charge minus q, we set the spring to oscillation, not only electromagnetic waves will be created, because q and minus q forms a dipole moment, and if the spring is oscillating back and forth, the dipole moment changes with time, and you from your Maxwell's equation, you know that the electromagnetic power is 2 by 3c cube multiplied by d double dot dot d double dot, where d is the dipole moment. The double dot is second time derivative. So when the dipole moment changes, or in other words, the charged particles accelerate, they radiate electromagnetic waves, but Einstein's theory says that because these two create a quadrupole moment of mass, and quadrupole moment is changing, there will be also a gravitational wave. That was what Einstein predicted, and therefore we know that if two objects go around each other, quadrupole moment is changing, they will create gravitational waves, which are nothing but ripple in the space-time geometry. If the surface of a neutron star oscillates, that will also create gravitational wave. If a star explodes into supernova, like this crab supernova, that will also create gravitational wave. If two neutron stars, which are orbiting about the common center of mass, because quadrupole moment is changing, they radiate gravitational waves, and gravitational waves carry away energy. If they carry away energy, the orbital energy of the neutron star is decreasing, and therefore, because orbital energy is decreasing, they are spiraling towards each other, and finally they will coalesce. And when they coalesce, so all through they will be emitting gravitational waves. When the neutron stars, which are stars made completely of neutrons, again this neutronics being the name of this physical society, has a nice connection with that. And with the two neutron stars, which have very high magnetic field, when they collide, they produce huge gamma rays, and there are short duration gamma ray bursts which astronomers have observed, and this is the model for how short duration gamma ray bursts are made. The gamma rays will be emitted in a narrow jet, and the central object can collapse to a black hole. Let me tell you that 3 days later, on October 16, there's going to be a big announcement from the LIGO group and the European Southern Observatory group. And whisper campaign, I mean it's not clear. So far, neutron star binary merging and producing gravitational waves have not been seen by LIGO detectors, but there is a whisper going on that on October 16, they probably will announce the first time discovery of gravitational waves from two neutron stars merging. And as I said, when two neutron stars merge, not only gravitational waves are produced, gamma rays are produced. So astronomers have also probably seen the ensuing gamma rays. So we'll watch out for October 16. By the way, gravitational waves were indirectly detected long time back, because as soon as Hulse and Taylor, they discovered the binary pulsar, which are nothing but two neutron stars going in orbit around the common center of mass, and thereby radiating gravitational waves and coming close by. And because they are coming close by, the period of their orbit keeps on decreasing, because major axis is also decreasing. As you know, Kepler's third law, cube of the major axis is proportional to square of the time period of a rotating orbiting system, and therefore the frequency of rotation, orbital revolution of the neutron star keeps on decreasing. By monitoring such a binary pulsar, Hulse and Taylor showed that they exactly follow the gravitational wave carrying away energy, and because of that they were awarded Nobel Prize in 1993. But it was an indirect detection. They have not directly measured the gravitational wave component. And we know that when big objects are compressed to size less than the Schwarzschild radius is nothing but 2 times gm by c square. So if you take mass of the sun, which is 2 into 10 to the power 33 grams, and calculate what is 2 gm by c square, you'll find this number is 3 kilometers. The actual size of sun is 6.96 into 10 to the power 5 kilometers. So it's not a black hole, but if you compress the sun from the present size of 6.96 into 10 to the power 5 kilometers to a size below 3 kilometers, the whole thing will collapse to a black hole. All mass will end up at a single point, density will become infinite, the space-time geometric curvature will also become infinite, and what you will have is a black hole, which is surrounded by a mathematical surface called event horizon, and anything that happens below the event horizon, you can never know outside, because even light cannot escape from regions within the event horizon. So these are all black holes, and as I have already mentioned, the first gravitational wave event that was directly detected, binary black hole or binary neutron star sources, but there are neutron stars. If it is having a hill on the surface, then as it rotates, again quadrupole moment will change and produce gravitational waves. People are searching for gravitational waves for such asymmetric neutron star. Then a star, if it's a massive object, when the nuclear fuel runs out, then it collapses and gives rise to a big explosion called supernova explosion, like Crab, or when I was still a PhD student at TIFR, a supernova explosion happened at Large Magellanic Cloud, the so-called supernova 1987. Such supernovae will produce huge amount of gravitational wave, and neutron stars, as I have already mentioned, there is an actual Chandra Observatory X-ray image of Crab pulsar, and you can see the amount of rotation, and such pulsars, which are neutron stars with very high magnetic field, more than 10^12 Gauss, rotating very fast, faster than a time period of few milliseconds, and such objects create great electric field because magnetic field is changing rapidly, and such electric field accelerate particles to relativistic speed, and we expect great amount of gravitational waves coming. So all kinds of supernovae will produce gravitational wave. And how do you detect gravitational wave? How did LIGO detect? As I said, gravitational wave is nothing but space-time geometry changing. So therefore, if you have a circular arrangement of test particles, when gravitational wave pass, the distance between them will change. So one side the distance will get elongated, the other side distance will get compressed, and after half a cycle reverse will happen. So if you have an interferometer, laser interferometer with a beam splitter here, two mirrors hanging, then the distance being changing will cause shift in the phase, and changes in the phase will create friendship, and that is how you are detecting gravitational wave. This is an aerial view of the LIGO detector. So the actual LIGO detector is in the Fabry-Perot mode, not in Michelson interferometer, because if you have Fabry-Perot cavity, that is two mirrors here in the arm, two mirrors in the other arm, they trap the laser and there is a resonant cavity. By trapping it, the effective arm length increases and sensitivity of the gravitational wave becomes more. So these are cutting edge experiments, and all kinds of things are happening. Quantum theory of light plays a very important role. I don't want to go into the detail. The light, when you quantize, uncertainty principle is there, phase and number of photons, there is uncertainty. Can we decrease the phase uncertainty? And that is where squeeze states of light are being planned to be used in LIGO detector. And right now, no one in India does research on actual experiments on squeezed light. So when LIGO India is going to be set up, people will research on actual. The first gravitational wave event that was directly detected was two black holes in a binary system radiating gravitational waves and eventually merging. Theoretically, such things were already known. Theoretically, one knew that whenever such a thing happens, the gravitational wave amplitude increases with time and wavelength decreases with time. I tell you why it should happen. Physically, you expect that. What is happening is the major axis is decreasing because gravitational wave is carrying away energy. But because of that, the velocity of individual black hole is also increasing. They are going faster. Why? Because v square by r must be gm by r square. So therefore, v square is gm by r. If r is decreasing, v is increasing. More the velocity, higher is the amplitude of the gravitational wave. And so gravitational wave amplitude keeps on increasing, the wavelength keeps on decreasing, and eventually when they meet, they become a black hole, and after that, when the black hole is settling down, it rings like a bell. These are all theory, by the way. Okay? But now comes the actual observation by LIGO, where they showed that two black holes, one which is 29 times heavier than Sun's mass, the other 36 times heavier than Sun's mass, they coalesce to form a black hole which is 62 times Sun's mass, and where did the addition will give you 65, where did that 3 solar mass disappear? That is the mc square, that is the energy which was carried away by the gravitational wave, and this is the actual data. So there are two detectors, one at Hanford, the other at the Livingston. Hanford detector saw this, Livingston saw this. If you subtract out the noise, this is pure noise, you see how well they match the theoretical calculation. Similarly, they plotted the frequency versus time, and you see the frequency increases with time. Just like what would happen when two binary black holes start merging.
And the two detectors, as I had said, this is a Livingston detector, this is a Hanford detector. The distance between them is about 3000 kilometers, and therefore if a light comes along this direction, first it will hit this and then it will hit, and because it's 3000 kilometers, the time delay will be how many seconds? 10 milliseconds. But for the gravitational wave that was detected, the time delay was 7 milliseconds. That means the wave front came somewhere like this. It came from this direction. The wave fronts first hit the Livingston, then went to Hanford, and the time delay was 7 milliseconds. And the detection did three very important things. What was that? The first thing, it gave strong evidence for direct detection of massive black holes. Then, when this was depicted, I immediately showed that the parameters derived from this is consistent with something called Hawking black hole area theorem, according to which if you take two black holes, event horizon area A1, event horizon area A2, and you combine the black hole to form a single black hole, Hawking had proved that the final black hole's area, that is A3 will be always greater than A1 plus A2. I showed that yes, the parameters which the first detection got indeed is consistent with black hole area theorem, but something more was confirmed is the so-called chirp waveform, where the amplitude goes up, frequency goes up. That was a theoretical calculation, it was confirmed. Then late Professor C.V. Vishweshwara, who was a faculty in RRI, Raman Research Institute, Bangalore, for a very long time, and when he was a PhD student in University of Maryland, USA, in 1970, he had shown that if you disturb a black hole, then the black hole rings like a bell with a frequency, characteristic frequency inversely proportional to 1 over mass. And as you can see, that ringing like thing has almost been seen, almost, although the amplitude is very low. So statistical confidence level is not very high, but the fact that such a thing is being seen shows that Vishweshwara, as a PhD student, was so right. Unfortunately, he is no more with us. And what is more important is that because of all these activities, the government immediately sanctioned the LIGO India project. So India will have the American people setting up a LIGO detector somewhere in Maharashtra, close to Aurangabad city, where Ajanta, Ellora, etc. are there. And the second gravitational wave was again merging of two black holes, but the masses were not so high, 14.2 solar mass, 7.5 solar mass, combining to form 20.8 solar mass, and about 1 solar mass was converted into energy. Right now we have 3 more candidates. These are the summary of masses. So the first candidate had the bigger mass, but recently in August there was a detection, again 25 solar mass and 31 solar mass. And not although as high as the first detection. You see, now we are having interesting phase. Finally what I will do is I will show some other types of gravitational wave sources. We have already seen binary black, the quantum theory of light directly visible when you are detecting gravitational wave. By the way, I must pay tribute to Joe Weber. He way back in 1960s was the first to create a gravitational wave detector, except the principle was different. That was a bar detector. He created a 1-ton aluminium bar in a cylindrical shape, solid aluminium bar. And the idea was when a gravitational wave comes, you excite the normal mode oscillation, and by looking at the oscillation you can detect gravitational wave. Unfortunately, his reputation went down a little bit when he claimed that he has seen some gravitational wave when other people did not see. In science, remember, one experiment doesn't tell you anything. You have to do more number of experiments to corroborate what someone has seen is correct or not. Where science is based on actual experimentation, not just imagining things. Imagination plays a role in model building, but ultimately science is what the world is really, not how the world is imagined. So therefore, in future, space-based gravitational waves are being sort of thought about, here is Earth, here is Moon, and people have shown theoretically that if you have 3 interferometers, each orbiting around Sun, then they can maintain a equilateral triangle configuration, and by laser light going from one detector to another, you can have very low frequency gravitational wave detected. So any gravitational wave emitted by a supermassive black hole orbiting can be detected by such things. But this project, so-called LISA project, has not yet been passed by American government. European, they are also making e-LISA, so we don't know whether they will be actually built. So for future, the world is all yours. Young people, we will all retire, die out, but for young people, the future is absolutely exciting and fascinating. Who would have imagined when we were college students, we never thought that there would be internet. We didn't have, no one, not even science fiction authors, could imagine that internet will revolutionize world, but it happened. What all exciting things are going to happen 10 years later, 20 years later, 30 years later, we can't even imagine. The world is progressing very rapidly. So you young people, and how is it progressing? Through reason, through logic, through mathematics, and through scientific experimentation. And you are right now on the throes of revolutionizing the entire future. So participate in it. Because human beings are the only beings who have brain, who can think. Use your thinking facility. All other things, emotion, etc., even animals have emotion. They are all nonsense. I would say that all your creative talent, music, language, thinking, science, these are very important. And when you are young, you can make this much more sharper. And after a particular age, it's like gymnastics. I can't learn gymnastics somersault in the air, but young people can learn gymnastics. Similarly, young people can do gymnastics of thinking, which is nothing but mathematics and physics. So I urge you to use the fact that we are human beings possessing powerful brain to that, because the world is going to be fantastic. We might not be there to see such a magnificent scientific world, but you will be there. So right now, get ready and enjoy what is happening, so that you can understand the mystery of the universe. You can understand the gravitational wave produced during the Big Bang. Hopefully, the space-based gravitational wave detection will show that, and finally understand what happened during the Big Bang. So there are many institutes in our country here which are part of the so-called Indigo collaboration, including Delhi University and the LIGO. So here is the website. More information on LIGO India will be, you can log in there, you can attend summer schools, winter schools, organize, and the whole challenge of a futuristic world is right before you. Thank you very much. Yes.
What's the benefit of this gravitational wave measurement? We are so much emphasizing on this. So what will be the future benefit of it?
Yes, the future benefits will be indirect. To give you an analogy, let me ask you the question, who invented internet? CERN, particle physicists in CERN. So therefore, although detecting Higgs has no benefit for human life, detecting supersymmetric particles, maybe they are there in future, will not directly benefit. But when you are doing cutting edge experiments, the spin-offs, the technology which comes out, revolutionize. So internet revolutionized the world. In LIGO, what are possible ways how we can see that we can do the squeeze states of light, which is being used to decrease the noise level. Noise is something which is unwanted. So if squeeze light can be used to decrease noise level, maybe they can aid in tumor detection. If you have very tiny tumor, the X-rays can't see it, they are so tiny. So maybe squeeze state of laser light, because noise level has gone down, you can detect it. So therefore, there are indirect benefits that can come up from the LIGO itself. If you build a very fascinating and very sensitive gravitational wave detector, suppose someone fires a missile towards India, the missile, again mass is redistributing, is coming closer, the gravitational wave experiment can detect it, and you'll be forewarned, and then you can fire an anti-missile to counter. So there are indirect benefits which you can't foresee. So very often people say that what is the benefit of theoretical research? These are all achievements of mind, and everything must be there because human beings have intelligence. Intelligence requires inspiration, it requires new fascinating things. That's why great literature is important, great movies are important. Movies, they immediately inspire us, great movies, inspire us like Satyajit Ray's movies or Shyam Manigal's movies. The art in the movie, the thought in the movie, they completely change our thinking. So these are the indirect benefits of the field of creativity.
Any other question?
First, really I'm so happy, so inspired to see all this. I think everyone future clapping monitor. आपको को ये पूछना चाहिए कि नोबेल प्राइज कैसे मिलना चाहिए तो that would be really great. Sir, I have one question because you have shown several cycles of gravitational waves and they are like successive things. I think they were separated by like 7 microseconds and time delay. Yeah, time delay. So finally, it looks like at the end the amplitude is increased, and then suddenly it's just like a breaking of wave system in the fluid system. It matches with that. Like you are having a density variation, and the density is decreasing, the amplitude is going to increase, and then suddenly it cannot, the inertia of the fluid system cannot support that, and therefore it basically breaks. So it matches with that, to tell you that, like matching with the fluid system, wave system, matching with this gravitational wave. So the last part seems to be like breaking and turning into a very small amplitude. So this is all happening as a result of the source, or
What is happening is, the breaking analogy is this, that when the two black holes are coming closer, they are becoming faster, because Keplerian law, V is equal to square root of Gm by R. So as R is decreasing, they are becoming faster, and once they are faster, the quadrupole moment is changing very fast, the amplitude of the gravitational waves is going up. But then eventually two things become a single black hole. But black holes don't radiate anything. So once something becomes black hole, now nothing can be radiated out. So therefore the black hole, till it settles down as a stable black hole, it radiates time. What is that Vishweshwara had discovered? So the ringing, the amplitude is small, but we still see ringing. But once it stabilizes into black hole, no more radiation, because black hole doesn't radiate anything. So this particular event, the black hole coalescence, was few seconds. So again, the black hole was emitting, the binary system was emitting gravitational waves for time immemorial. But the LIGO detector, that probably I failed to emphasize, the sensitivity of LIGO detector is only from about 40 Hertz to 1 kilohertz. So only when the gravitational wave, the frequency is increasing, when the frequency enters the band 40 Hertz and remains up to 1 kilohertz, only that part LIGO can detect. And that part for the first detection had few seconds. Yeah.
Thank you, sir, for speaking lecture. Sir, I have a doubt. We have discovered the electromagnetic waves, microwaves, to be using in day-to-day life. So, is there any practical way to use the gravitational waves? Because these are traveling at the speed of light and they are not obstructed by any more obstacles.
Yes. Supposing you can use gravitational waves. How is gravitational wave propagating different from electromagnetic wave. As you know, electromagnetic forces are 10 to the 40 times stronger than gravitational forces. So therefore, electromagnetic wave gets scattered. That's the reason why you only see the surface of the sun. What is going inside the sun you don't see, because the electromagnetic interaction, what is happening inside the sun, this can get scattered. So that's precisely the reason why we need a wave which is very weakly interacting. So therefore, if I want to send, supposing I'm talking about future, after let's say 300 years, 400 years, when human beings settle in distant star, and now we know exoplanets have been discovered. Eventually, sun will explode. Rather, it will not explode. It will become a red giant and finally become a white dwarf. So when it becomes red giant, it expands. Earth will be swallowed. So we need to therefore move away. So our future generation move to distant stars. Some people will remain in one planetary system here, some people. How do they communicate? So if they have powerful gravitational waves, they can communicate with each other without fearing loss of signal to noise ratio, which happens for electromagnetic waves. But these are all future, 100, 200, maybe 1,000 years after that we will be that technologically. But there's no hurry. After all, sun will become a red giant only after a billion years.
There are two headquarters at Albania and the USA. So you discuss.
These are all in US.
Yes, sir.
Livingston and Westport.
Yes,
There
sir.
are East Coast and West Coast.
But sir, they are 3,000 kilometers far away. Light takes 10 milliseconds. You know, so light takes time to cover distance. The time like between the light from this point to this point.
From Livingston to Hanford,
Yes, sir.
along this line, light will take 10 milliseconds.
10 milliseconds. But the gravitational waves take 7 milliseconds. So how is this possible? So no one can travel faster than the speed of
Go
light.
back to the picture. Yeah. So light, if it goes from light or gravitational wave, they all move with speed. If the gravitational wave source was exactly collinear with the straight line, it would have taken 10 minutes. But suppose the gravitational wave sources, then gravitational black holes merge during gravitational wave. So the plane wave will come like this. Plane wave, plane wave, plane wave. Plane wave will strike this. So you will see the first gravitational plane wave, plane wave. But this plane wave is not moving along this line, it's moving from this line. That distance is shorter.
Or they are according to suspense relativity, no one can know the speed of light.
Sir, okay, I have one more question, sir. From our primary classes, we have read like wind. Wind is a flow of air from one place to another places due to a pressure difference. And now we have two things. One electromagnetic wave that is so abundant in nature, like produced or naturally happens. And second is gravitational waves. Also, we know that it is very like nature possible to detect very easily. So electromagnetic waves have not disturbed the course of wind, but we can consider winds are there are air molecules which are flowing from one place to another due to pressure differences. So it can it happen like gravitational waves can affect the course of wind, like a western eyes can change to western eyes like that, because there are
Gravitational wave amplitude here is so low.
yeah.
Even by the way, I didn't put the numbers. The LIGO,
When gravitational wave went by, the change in the distance between the beam splitter and the mirror, the change was a fraction of a neutron or a proton. The change in the length. So that is why it took 100 years to do the detection. The gravitational waves, although the powerful gravitational waves are emitted by the two binary black holes, the distance is about 1.3 billion light years. By the time the gravitational wave comes, the amplitude goes as 1 over distance. The amplitude is very tiny. So this tiny amplitude, it can only, even if you have a 4 kilometer long distance between beam splitter and one mirror, the chain will be only about fraction of a proton diameter. So therefore, wind will hardly get affected by the passing on. Yeah, there will be an effect, but that effect is much less compared to any other effect like temperature variation or Earth's changing gravitational field. These are much more dominant. In physics, but these are important questions. A good experimentalist must be able to figure out which are the dominant physical effects that affect your measurement and which are not so dominant. That is what the training one must get when one is doing good experiments.
Sir, in physics we know that every wave interacts with matter. So how gravitation waves interact with the matter in surrounding?
So, gravitational waves, as I said, is ripple in space-time geometry. So the way it interacts is slightly different. It is purely geometry. Because Einstein showed in general theory of relativity that there is no force called gravity. Rather, it is a changing space-time geometry which appears to us as a force. So therefore, gravitational wave is basically when a gravitational wave goes by, the space-time geometry changes. So what is geometry? Geometry is all about measuring distances and angles. So therefore, in order to know the change in geometry, I have to see how the distances change, how the angles change. So therefore, the effect of gravitational wave is that if you have initially test particles arranged in a circle, then when the gravitational wave goes by, for the first half cycle maybe in this direction the distance will decrease, in that direction distance will increase. Next half cycle, the distance between these test particles will increase and the distance between these two particles will decrease. So this is the effect of gravitational wave on test particles. The distances will change with space and time, because gravitational wave is nothing but a ripple of space-time geometry changing and propagating.
So,
Yeah.
so as you have said that it will be, it has taken such a long time, and initially the amplitudes would be very, very large, but it takes time and the amplitude decreases as it's coming along. So then it would have done maybe changed so many motions in the galaxy, or maybe it would have done.
Now, as I said, that the gravitational wave amplitude, where the two black holes merge, there will be strong.
Yeah.
So near the merging of the black hole, the gravitational wave would have affected the stars nearby,
Exactly.
the density of, but that is already 1.4 billion light years away.
Right.
By the time it hits the Milky Way, the gravitational wave has become very weak. So it will hardly do anything to our Milky Way galaxy.
But maybe it would be affecting some other galaxy in a more.
Very, very in its own neighborhood. Remember,
In its own
the
neighborhood.
gravitational wave amplitude goes at 1 over distance.
Yeah.
So therefore, even 1 over d being a typical size of a galaxy, typical size of a galaxy is about 20 into 10 to the power 3
Yeah.
into 3 into 10 to the power 18 centimeters. So you can see it's about 10 to the power 22 centimeters. When you divide something by 10 to the power 22 centimeters,
Amplitude becomes very small.
amplitude becomes very less. So therefore, near the two black holes that merge, yes, there the effect was very severe. That means within about 10 to the power 10 centimeters, very severe. But as you grow, as they go out of its own galaxy has a size of 10 to the power 22 centimeters, the amplitude decreases. So no effect. So that's why gravitational wave goes being almost transparent to everything.
So can we say in that sense then the event of horizon is pretty large in this case, as you have said the event of
Event
horizon?
of horizon is there only for black hole.
Only for the
So the black hole, 36 solar mass, the event horizon size is 36 into 3 kilometers. 29 solar mass black hole, its event horizon has a size 29 kilometers into 3. So they are only around the respective black hole. But once the thing has escaped out of the black hole, now the event horizon doesn't play any
Doesn't
role.
play. Okay. Thank you, sir.
Yeah.
Since we are talking about waves, what is the relevant wave equation?
Yeah, box. Yeah. So I skipped because I didn't want to go into the mathematics of it. It is exactly the box of the amplitude equal to 0. I don't know where it is. Yeah, here it is. So actually there should be mu. So box operator is 1 over c square del 2 by del t square minus square of grad square, that is Laplacian. So it's exactly like the box operator in electromagnetic wave. There's a mistake, it should be h mu. So in vacuum, the gravitational wave amplitude h mu satisfies the result that the box operator or the de-Lavoisian operator acting on h mu is simply 0. That's why it propagates with speed c. Just like electromagnetic wave also box of electric field is 0. Or box of magnetic field is 0.
Dirac equation?
No. Dirac equation is linear in space-time derivative. Dirac equation is alpha dot grad operator plus beta mc square acting on psi is 0. Yes, sir.
Galaxy has a typical size. How we get to know that the gravitational waves are coming from Schumacher's? Sir, as you have just said, the galaxy has a typical size, and there are many galaxies. Then how we get to know that the gravitational waves are coming from the black holes only? There may be another source also.
A lot of theoretical modeling is required. So first, you have done theory. So
Again, astronomy and astrophysics, you can only observe, you can't do experiments. See, remember one thing, there's a difference between the way one does astrophysics and the way one does laboratory physics. In laboratory, you can do controlled experiments. Supposing I want to study the magnetoresistance of a substance. What is the magnetoresistance? I want to see how the resistance of a sample changes when I apply magnetic field. In the laboratory, I can do a controlled experiment. I take a sample, put it in 10 gauss, 20 gauss, 10 is for 5 gauss, and study how the resistance changes with magnetic field. I can do controlled study. But when something is very far away, from moon onwards, I can't go there and do experiment. I can only study what the nature itself offers us. So I have to see what is unusual. And therefore, in astronomy, astrophysics and space science, the way to deduce things is first do theoretical calculation and see what is expected. And then you observe. So what was expected was that if you have binary source, then if you have two mass points, what is expected is all theory. What we expect is when you have a binary source, we assume, law assumption, we assume that there are two mass going around, then theory will tell us that there will be gravitational wave amplitude going on. But these are all theory. As I said, when in science, theory plays a role, but ultimate test of the theory is experiment. Remember that. That is why astrology is not a science, because this prediction is never true. Just an example. So, therefore, these are all theory. But then, is this theory correct? Then you have to do actual measurement. These are actual data. There is actual signal from the Hanford detector. There is actual signal from the Livingston data. Fortunately, the first detection, the black hole masses were so large that actual signal was much bigger than the noise. So you can directly see that it looks so similar to the theoretical calculation. And then you do something called a match filtering technique. Those who are doing electronics, maybe in the signal analysis, you might have done a powerful technique which radar experts use, something called match filtering technique. That means, how do radar people deduce that there is an aircraft, supersonic aircraft coming from somewhere going? The supersonic, till you hear the sonic boom, you don't know, it has already gone there. But radar people, they first theoretically calculate if such a plane goes by, what kind of radio waves it will send. then when the actual radio waves come, they do a cross correlation between your template and the actual. That's called match filtering technique. Those who are interested in data analysis in gravitational wave, a lot of people are doing it, and there's a lot of job opportunities with LIGO India. And match filtering technique is also a very interesting technique. I have written one article on match filtering, how you do it from physics point of view. That article is there in the Indigo website somewhere. You can search and get it. It's a very interesting technique, and it's an engineering technique. But engineering techniques are very important in experiments like LIGO. So first you do theoretical modeling for astrophysics, and then you take a signal and say, oh, this signal, does it agree with my theory? Then you do data analysis. If it doesn't agree with your theory, experiments are more important. You change your theoretical model. That's how science progresses.
Thank you so much, sir. Now I'd like to request Dhaka sir to come onto the stage and give word of thanks.
I would like to thank you, Professor Patrick Das Gupta. हम प्यार से सब लोग उनको पैट्रिक सर बोलते हैं तो पैट्रिक सर ही बोले थे सर आई थिंक वी आर मोर कंफर्टेबल आई थिंक एक बार बहुत जोरदार तालियों से उनका so like जब मैं उनसे कांटेक्ट किया maybe like 2 weeks ago and after 3 days we came to know that Nobel Prize winner is topic. Maybe topic already we decided. So we never knew that maybe after 1 week the entire group team will receive the Nobel Prize. So we are really blessed today, sir. And you said yes, and you came here all the way. I knew that maybe you will be too busy somewhere, but you really spared this particular time for Rajdhani College. And we are very lucky you have been here, and you guided us even in the past. And we believe that we would like to see you again in the near future. So thank you very much once again, and I would like to thanks to my old colleagues sitting here, Dr. A.P. Singh, Sangeeta, Sunita, Saraswati, and सारे लोग बैठे हैं, especially एक बार मैं स्टूडेंट्स के लिए इतना शांत उन्होंने सुना मुझे उनके प्रोग्राम के बच्चे समझ रहे हैं मुझे really glad for our side. And thanks this young team. Sir, I assure you that maybe 10-15 students from physics of this final year will join master course and doctor course because उन्होंने मुझसे कई बार promise किया कि वो काफी बच्चे यहाँ से master course के लिए जाएंगे. Razmil is here. I would like to thank to him, Karan, and Andrila, Navneet, and Megha, and many more. Come to the 20 students, and they are so nice, so kind. I really love them. मैं क्या कहूँ मुझे बहुत सच में ये I think after a few years we are having very good students, really. Thank you very much. And having discussed, and I hope that we will have more programs for the Physics and Electronics Society in the near future, and that will be a little bigger, maybe the whole day and the 2 days program. Sangeeta, Sunita, I think you also think about some design of the program for 1 day or 2 days. So thanks a lot, thank you sir. And now we disperse, and I would request our teachers to go to the NXC. We will have some snacks or food. And thanks students, we will have some big program later for you. Thank you.